Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. I'm talking about amines, and when I say amine, mainly primary, secondary, or tertiary amines. And any of these amine has a lone pair. That means they can get involved in SN2 reaction, and one of the reaction is going to be reaction of amine with acyl chloride, and that's gonna give us amide. Or and we take we remove technically one of the hydrogens, and now we will pair the nitrogen with carbon. That carbon here is attached to oxygen and a plus, let's say CH3, for example. So now we got a connection between nitrogen and a carbonyl group, and that's gonna give us an amide. Now, that lone pair, it can do resonance, and it can build a double bond with carbon, and if that one happen, we get such a product. Double bond here, we have an H. This one, it will have a positive charge, and now carbon, it will give up those two electrons. They will be located in oxygen. Not oxygen, it will get a negative charge, and here we get CH3. Okay, so as you see, the lone pair in amide is involved in the resonance structure with a carbonyl group. So it's not that strong base because it already shared the lone pair with the carbonyl group. So what I want to say, if you take an amine group and turn it to amide, it will be a weaker, okay, a weaker electron donating group. So it will be a weaker electron donating group. Okay, and we're gonna use this technically properties or this benefit to control some chemical reactions. And one of the reactions that I want to talk about is going to be a bromination of aniline. And if you don't have any control to this reaction, the product is not gonna stop on one monobromination, and in fact, actually, it will go 3 steps more and 2 steps more, and it will give us a tribromoaniline. So how do I control this reaction? And how do I control this reaction in order to get only bromoaniline? In order to do it, we're gonna technically block the aniline, the amino group through reacting it with acyl chloride. So this is gonna give us nitrogen attached to carbonyl group. Here we have CH3. And yes, we do have one hydrogen. So instead of 2 hydrogen, now we have only one. And there's one lone pair. Next step, we're going to treat it with a bromide. Okay. And until now, what did we get? What did we change? Okay. Nitrogen, the nitrogen and aniline, it can easily share the lone pair with the ring, and it will increase the negative charge inside the ring. So it will enrich the ring. Well, when you attach a carbonyl group to nitrogen, because this one, it has sp2 hybridization, it will pull some of the electron density to itself. So it's not going to let nitrogen to share entire of that lone pair with the ring. And I'm going to say, yes, we do get negative charge, but not much. Okay, not much. And now bromide, it will reach the ring. And so let's say we're going to get Br as the Br plus as the electrophile. And this one will be added in a para position, and we get the bromide here. And what do we have there? NH attached to carbonyl group. And next step, we're gonna release this part of the product, But in order to release it, we need to use a harsh condition. We need to go with a strong basic solution or acidic solution. And any method is not going to be a friendly method for environment. But if you use acidic or basic condition, amide bond, very soon it will be broken, and technically it will turn to NH2. So this one, it will be NH2. We get the amine back, and we have in the para position, we have bromo there. So now we managed to get mono bromo product instead of a tri-bromo product. And this is the benefit of using oscillation, the oscillar group to protect or to block the NH2 group. And that way, we reduce the electron donating character of the NH2. Okay. And last thing that I want to talk about is going to be the elimination. Similar to alcohol, you can take amine compound and turn it to alkene. And so NH2, it will leave the system and it will give us a double bond. In order to take NH2 out of the system, we need to make it a good leaving group. NH2 is not a good leaving group, but if you treat it with excess amount of alkyl halide, we know it's going to go extreme, and it will replace the 2 hydrogen and 1 lone pair by 3 alkyl groups. So technically, we get a quaternary amine. And now nitrogen, it has a positive charge, and because it has a positive charge, it will be a good leaving group. But in order to leave the group, leave the system, has to take those 2 electrons, and then it will leave the system. So it's going to leave carbon with a positive charge, technically. Now, depends what you use. You can replace it by substituent, or you can do an elimination reactions. And for example, if you use a strong base, it can take hydrogen from any of this carbon, and it will give us a double bond. And for this purpose, we can use silver oxide as a base to remove hydrogen from the system. And if we run such a thing, we get this product, NH2. It will leave the system as, technically, it will leave the system as N and methyl 3 times. Nitrogen will have a lone pair, and also we get an alkene. Now, I want you to look to the position of the double bond. The double bond is showing as terminal. That means that's a Hofmann product. And our base is not that strong, it's not that bulky base. So the question is, why do we get terminal alkene instead of Zaitsev? We said Zaitsev thermodynamically is more stable than Hofmann product. So why do we get Hofmann instead of Zaitsev product? And that's the subject that I want to go after it. So if we treat it with excess of alkyl halide, we know we can turn it to a quaternary amine. And next step, if we introduce it to a strong base, the strong base is going to run the reaction and or push the reaction through an E2 mechanism. So we get alkene as a final product, and the double bond, if it's terminal, it will be a Hofmann product. If it's say going after this hydrogen, okay, so instead of this beta 1 hydrogen, we go after beta 2 hydrogen, then we get Zaitsev product. I know Zaitsev product, or we know Zaitsev product is more stable than Hofmann, but Hofmann is going to be the major product. This one, it will be the minor product. Okay, I want to know why Hofmann product is going to be the major one. So let's look to the difference between those 2 hydrogens that I labeled. This one is that hydrogen, and we're going to call it beta 1. And this hydrogen, we're going to call it beta 2. And okay, or forgive me, because the way we're looking to the bond, this is going to be this hydrogen is going to be beta 2, and this hydrogen, the sitting number, carbon number 1, the hydrogen, and it will be the beta 1. Okay, I know for E2 elimination, position of the leaving group, which is this one, leaving group, and hydrogen must be in anti-position. They must be 180 degrees far from each other. So I'm going to put the leaving group, and hydrogen in 180 degrees far from each other. Now, if we look through carbon number 2 to carbon number 3, on carbon number 2, we will see a leaving group, and also we will see a methyl. Put the methyl wherever you want, okay? So put the methyl wherever you want. So let's say I put the methyl here. What else I have on this carbon? Okay, on that carbon, I have a methyl and also one hydrogen. Let's say we're gonna put the hydrogen there. Okay, so I do have a hydrogen, and that hydrogen, it can be anywhere. So there's hydrogen. Next, what do we have on carbon number 3? Carbon number 3, we have 2 hydrogens. Okay, one of the hydrogen, I put it in anti-position relative to the leaving group. Now, the second hydrogen, wherever you want to put it, is up to you. So say I put that hydrogen here. Now, I'm left with an isopropyl group. Forgive me. I'm left with an isopropyl group. This is the isopropyl group. For the propyl group, my bad. So I get, let's see, 1, 2, 3. Okay. Or I can say we got CH2, then CH2, and then CH3. That's one case. Okay. If we look to carbon number 2 to carbon number 1, okay, the front one, it will be carbon number 2. Carbon number 2, we have, again, we have hydrogen and a leaving group. So one hydrogen, and then the hydrogen on carbon number 2, I'm going to put it, for example, here. Let's go with a black color. And what else we have? This time we're going to have this. Wherever, again, you want to put it is up to you. You want to put it right or left. Okay, I'm going to put it on the left side. So I get CH2, 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 and then CH3. So now I have butyl, technically, instead of propyl. And what else? On carbon number 1, I have 3 hydrogens. And here you go, 3 hydrogen. Now I want you to zoom on these regions. Okay, we have a propyl group and a leaving group there. Well, this is our leaving group. And neighbor to it, we have only hydrogen, 2 hydrogen atoms. And I know the leaving group must be in anti-position relative to the hydrogen. Okay, because the base, any base that we use, let's say we use OH, OH is going to go after this hydrogen. And it will take that hydrogen, and then leaving group, it will leave the system. Now, in both cases, I have hydrogen anti-position. What's the problem here? The problem, okay, number 1, if we take hydrogen from carbon number 3, we will have gauge interaction. Gauge interaction between leaving group and the propyl group. While if we take hydrogen from the terminal carbon, we are not going to get any gauge interaction. So no gauge interaction. And because we don't have any gauge interaction, and removing hydrogen from the terminal carbon, it will be favored. And so this one is going to give us technically such a product. So we're gonna get, I'm gonna write it down here. We will get half an product, while the top one will give us Zaitsev product. So we get this. And I said, this one is gonna be the minor, and that's gonna be the major. So as you see, the main problem with the Zaitsev product is inside the transition state, we will have gauge interaction between the leaving group and one of the substituent, which we don't have it if we remove hydrogen from the terminal carbon. And this is the reason that the mechanism will go through Hoffman pathway rather than Zaitsev pathway. And thank you very much.